We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
Namaskar. Today we learn about the subject is Advanced Separation Techniques, and our topic is Advanced Separation Method. The content is Introduction, Types of Advanced Separation Method, in Advanced Separation Method, Membrane Separation Method, Supercritical Fluid Extraction. Introduction of Advanced Separation Techniques is, in chemical and chemical engineering, a separation process is used to transform a mixture of substances into 2 or more distinct products. Then, separation applications in the field of chemical engineering are very important. A good example is that of crude oil. Advanced separation method is recently used in all chemical industries and also all over the industries. Basics of membrane separation technology. A membrane separation system separates an effluent stream into 2 streams known as permeate and the concentrate. The permeate is the portion of the fluid that has passed through the semi-permeable membrane, whereas the concentrate stream contains the constituents that have been rejected by the membranes. Types of advanced separation method. The types of advanced separation method is membrane separation method, supercritical fluid extraction, and reactive distillation. If you thinking about the membrane separation method, the membrane separation system separate an effluent stream into 2 effluent streams known as the permeate and concentrate. The permeate is the portion of the fluid that has passed through the semi-permeable membrane, whereas the concentrate stream contains the constituents that have been rejected by the membranes. So if you seen in the flow sheet, or if you seen in the your figure, you can see you can easily identify how the permeate can come out and retentate can go back. So based on the pressure and based on the size, the separation is occur in membrane separation techniques. Then after, if you thinking about another separation method, the separation technology cover all the process engineering measures for the transport of substance between 2 fractions with the help of permeable membranes. That means in the general mechanical separation process for the separation of gaseous or liquid stream using membrane technology. According to the driving force of the operation, it is possible to distinguish based on different operations. One of the operation is pressure driven operation, then concentration driven operation, then operation in electric potential gradient, then operation in temperature gradients. So examples of pressure driven operation is microfiltration, ultrafiltration, nanofiltration, reverse osmosis, gas separation, and pervaporation. And in concentration driven operation, the example is dialysis, osmosis, and forward osmosis. Then after, next is operation in electric potential gradient, and this example is electrodialysis, membrane electrodialysis, then electrophoresis. And next one is operation in temperature gradient is membrane distillation. So membrane separation process have very important role in separation industry. Nevertheless, they were not considered technically important until mid 1970. Membrane separation process differ based on separation mechanism and size of the separate particles. The widely used membrane process include microfiltration, ultrafiltration, nanofiltration, osmosis, electrodialysis, dialysis, electrodialysis, gas separation, vapor permeation, pervaporation, membrane distillation, and membrane contactors. All processes except for evaporation involve no phase change. All processes except electrodialysis are pressure driven. Microfiltration and ultrafiltration is widely used in food and beverages processing, in biotechnological application, pharmaceutical industry, water purification, water treatment, microelectronic industry, and others. Nanofiltration and reverse osmosis membrane are mainly used for the water purification purpose. Dense membrane are utilized for gas separation and sometime in membrane distillation. The latter process help in separation of isotopic composition, reducing the cost of distillation process. We are discussing different type of advanced separation method one by one. So in this one of them advanced separation method is reverse osmosis. Reverse osmosis is working on the principle of pressure. The pressure is osmotic pressure. Osmotic pressure, based on the osmotic pressure, the reverse osmosis work. Unlike water purification that can only remove some suspended materials larger than 1 micron, the process of reverse osmosis will eliminate the dissolved solid, bacteria, virus, and other germs contained in the water. The RO is generally used for the desalination seawater for its conversion into potable water. The silent feature of the process are that it involves no phase change and it is relatively a low energy process. Reverse osmosis and RO membranes. Reverse osmosis, often abbreviated to RO, is a technique employing a membrane which is semi-permeable, that is, under the influence of pressure a large proportion of water passes through the membrane then do the dissolved salt or organic molecules. The such semi-permeable membranes are common in the nature. The skin is good example, and this phenomena osmosis explain why you get thirsty as you swim in the sea or plump up in a long fresh water bath. So this is the example of semi-permeable membranes. Okay, so in the figure you can see that the first step is osmosis. In the first osmosis, low concentrated solution goes to the another side from the semi-permeable membrane. Then second one is osmotic equilibrium. In this equilibrium condition, the osmotic pressure that can equilibrium to each other. And third one is reverse osmosis. In the reverse osmosis, the concentric osmotic pressure is created and then separation is occur. The two material make up the bulk of commercial RO membrane. Cellulose acetate and aromatic polymer polyamide is the material of membranes. Reverse osmosis membranes do not have definable pores in the way that the films used in the ultrafiltration do. There are only space between the fibers making up the film, which can take up water because of the acetyl or similar grouping which form the surface. The dense layer of active surface is about 0.25 micron thick, supported by a thicker porous layer. The water in the space between the fibers has a short range order which each water molecule is placed so that the oxygen atom occupies the vertex of a tetrahedron and the hydrogen bond connect each pair of the molecules. This is an ice-like structure. The ice, it is of course continuous in liquid water at room temperature. Above half of the molecules are at any one time in such cluster. When the pressure is applied to the membrane, molecules on the high pressure side are incorporated into ice-like structure, replacing molecules which melt away on the other side. Iron in water surrounded as they are by water molecules aligned to shield the ionic charge cannot be made to fit into the ice-like matrix. Membranes are cast in thin sheet or extruded as hollow fibers about 80 or 250 micrometer in diameter. The advantage of hollow fiber configuration is that a very large surface area can be packed into a small space because the fibers, although a very small diameter, are technically thick-walled and so self-supporting. Cellulose acetate and polyamide membranes are used in RO membrane. Then another membranes can be used, but that is not acceptable, or they have. So normally you have to choose the proper membrane for different type of membrane materials. Application of reverse osmosis. So normally RO is used in each and every house for the purification. So normally in household for the potable water we can use the RO. So normally it is one type of application, but this RO can be used in each and everywhere, either it is a household or it is a industrial. So application of RO is extensive applications. One of them is potable water from sea or brackish water, ultra pure water for food processing and electronic industries, pharmaceutical grade water, water for chemical, pulp and paper industry, and water treatments. So normally each and everywhere we are using the reverse osmosis. And another one is future direction for RO application. So normally this RO recently we are using, but in the future we can also go for it. Okay, so normally one of them is municipal and industry water treatment, process water for boilers, dewatering of water streams, and processing high temperature feed streams. So this is the application of reverse osmosis. The next advanced separation method is ultrafiltration. Ultrafiltration is a variety of membrane filtration in which hydrostatic pressure force a liquid against a semi-permeable membrane. So normally this ultrafiltration is working on principle is hydrostatic pressure force. In this ultrafiltration, suspended solid and solute of high molecules weight are retained, while water and low molecular weight solute pass through the membrane. This separate process is used in the industry and research for purifying and concentrating macromolecules that size is 10 raised to 3 to 10 raised to 6 Da solutions. Da, that means Dalton, especially protein solution. Ultrafiltration is not fundamentally different from microfiltration, nanofiltration or gas separation, except in terms of the size of the molecules it retains. So normally different type of filtration unit is working on based on size. So here it is, different pore size of membrane material are used for the separation. So here the pressure is also different, their sustainability capacity is also different, their permeability capability is also different, then retentate capacity is also different. So ultrafiltration is applied in cross flow or dead end mode, and separation in ultrafiltration undergoes concentration polarization. Ultrafiltration is most commonly used to separate a solution that has a mixture of some desirable component and some that are not desirable. Their reject species include sugar, biomolecules, polymers, and colloidal particles. Ultrafiltration process operate at 2 to 10 bar through, in some cases up to 25 to 30 bar have been used. Ultrafiltration used implies separation of micromolecules such as protein from low molecular weight solvent. Ultrafiltration modules have used different type of modules. The modules is the one of the supporting role in the filtration. Based on the modules, the membrane and filtration is work out. So module is the one important part in filtration. So normally when we use the any type of filtration, you can also select the membrane modules and you can also select the membrane materials. So here is a ultrafiltration module configuration is pressurized system or pressure vessel configuration. So this is the transmembrane pressure is generated in the feed by pump, which the permeate stays at atmospheric pressure. Pressure vessels are generally standardized, allowing the design of membrane system to process independently of the characteristics of specific membrane elements. Application of ultrafiltration. First one is oil emulsion water treatment, treatment of whey in dairy industry, electrocoat, paint recovery, concentration of textile sizing, concentration of galanite, enzyme and pharmaceutical preparation, pulp mill waste treatment, production of ultra pure water for electronics industries. The next advanced separation method is nanofiltration. Nanofiltration is the form of filtration that uses the membranes to separate different fluids or ions. Nanofiltration is typically referred to as loose RO due to its large membrane pore structure as compared to the membranes used in RO, and allows more salt passes through the membrane. Because it can operate at much lower pressure and passes some of the inorganic salt. The advantage of nanofiltration over reverse osmosis is that nanofiltration can typically operate at higher recovery, thereby conserving total water usage due to a lower concentrate stream flow rate. The next filtration is microfiltration. Microfiltration is a separation technique for removing micron size particles like bacteria, yeast cell, colloids and smoke particles from suspension or gases. The process used membrane filters which pore is the approximately size range is 0.1 to 10 micron meter, which are permeable to the fluid but retain the particles, thus the causing separation. The microfiltration membrane are made from natural or synthetic polymers such as cellulose nitrate or acetate, polyamides, polysulfones, polycarbonate, polypropylene. The microfiltration is the process of filtration with micrometer size filter. The filter can be in a submerged configuration or a pressure vessel configuration. They can be hollow fiber, sheet, tubular, spiral wound, hollow fine fiber or track, etc. These filters are porous and allow water, monovalent species like Na plus and Cl minus, then dissolved organic matters, small colloidal and virus through, but do not allow particles, sediment, algae or large bacteria through. Microfiltration systems are designed to remove suspended solid down to 0.1 micrometer in size in a feed solution with up to 2 to 3% in the concentration. It is very suitable for use in place of traditional classifier or as pre-filter to a water recycling or recovering reverse osmosis system. Application of microfiltration is in biotechnology for concentration of biomass, separation of soluble products, then a diatomies or displacement, then next in non-sewage waste treatment for removing intradable particles in oily fluids, aqueous waste which contains particular toxics and stick gas, in paints for the separating solvent from pigments. The next advanced separation method is electrodialysis. The basic principle of electrodialysis, this is an electromembrane process in which the ions are transported through a membrane from one solution to the another under the influence of an electric potential. Electrodialysis is used widely for production of potable water from sea or brackish water, and electroplating, rinse, recovery, desalting of cheese whey, production of ultra pure water, etc. Electrodialysis is used to transport salt ion from one solute through the ion exchange membrane to another solution under the influence of an applied electric potential difference. This is done in configuration called as electrodialysis cell. So this is the definition of electrodialysis. This cell consists of feed compartment and concentrate compartment formed by an ion exchange membrane and cation exchange membrane placed between two electrodes. In almost all the particle electrolysis process, multiple electrolysis cells are arranged into a configuration called as electrodialysis stack with alternating anion and cation exchange membrane forming the multiple electrodialysis cell. Electrodialysis processes are different compared to distillation technique and other membrane based process in that dissolved species are moved away from the feed stream rather than the reverse osmosis. Because the quality of dissolved species in the feed stream is far less than that of the fluid, electrodialysis offer the particular advantages of much higher feed recovery in many applications. The next separation is gas separation. The membrane gas separation technology is over 10 years old and is provided to be one of the most significant unit operation. The membrane gas separation has been used for the hydrogen separation and recovery, ammonia purge gas, refinery hydrogen recovery, syngas separation in petrochemical industry, CO2 enhanced oil recovery, natural gas processing, air separation, nitrogen production, air dehydration, helium recovery, etc. So in gas separation, gas mixture can be effectively separated by synthetic membranes. For other method, see adsorption, cryogenic distillation is done. But in this case, in this gas separation, the gas is separated out. Usually non-porous polymeric membranes are used. In the figure you can see that usually non-porous polymeric membrane are used. The vapor and gas are separated due to their different solubility and diffusivity in the polymers. The permeability or permeation coefficient of such non-porous membrane can generally be expressed as a solubility. Solubility of gas in the membrane polymer multiplied by the diffusivity of the gas in the polymer. So that is called solution diffusion module. So this gas separation method is based on solution diffusion module. Next separation technique is pervaporation. This is a membrane based process for the separating miscible liquids. Pervaporation differs from all other membrane process because of phase changes of the permeate and non-porous. Transport through the membrane is affected by maintaining a vapor pressure gradient across the membrane. The pervaporation has been used for the separation of ethanol water mixture, solvent recovery, separation of heat sensitive product or enrichment of organic pollution, etc. The pervaporation technique, the name, of this membrane based process is derived from the two basic steps of the process. Firstly, the permeation through the membrane by the permeate, then its evaporation into vapor phase. This process is used by the numerous industries for the several different processes, including purification, analysis. Due to its simplicity and inline nature, the membrane acts as a selective barrier between the two phases, the liquid phase feed and the vapor phase permeate. They allow this desired components of the liquid feed to the transfer through it and by the vaporization. Separation of the component is based on difference in the transportation rate of individual component through the membrane. The next separation technique is supercritical fluid extraction. The basic principle of supercritical fluid extraction is that when the feed material is connected with a supercritical fluid, then the volatile substance will partition into supercritical phase. After the dissolution of soluble material, the supercritical fluid containing the dissolved substance is removed from the feed material. The extracted component is then completely separate from the supercritical fluid by means of temperature or the pressure change. The supercritical fluid is then may be recompressed to the extraction condition and recycled. The carbon dioxide and water are the most commonly used solvent for the supercritical fluid. So in the flow sheet you can see that the process is going on, how the process is going on. So let's explaining how the supercritical fluid extraction is work out. The procedure is that the system must be contain a pump for the CO2. In this figure you can see that the pump is there, a pressure cell to contain the sample, the means a means of maintaining the pressure in the system, and collecting the vessel. So normally you can see that in the figure different chambers are there. One of the chamber is CO2 pressurized chamber, another one is supercritical fluid extraction unit. So the liquid is pumped into heating zone where it is heated to supercritical conditions. So normally in this condition we want supercritical fluid. Based on the supercritical fluid extraction, the process is going on, otherwise the extraction is not possible. It then pass into the extraction vessel where it rapidly diffuses into the solid matrix and dissolve the material to be extracted. The dissolved material is swept from the extraction cell into a separator at low pressure and the extracted material is settled out. The CO2 can then be cooled, recompressed and recycled or discharged to the atmosphere. So in this basis the process is going on. Industrial application of supercritical fluid extraction. Normally it is not a simple extraction, it is a supercritical fluid extraction. So normally this type of extraction unit is used for the extraction. So one of them separation extraction is food and flavoring industry, then petrochemistry, then pharmaceutical industry, then other plant extraction unit, then environmental protection. The next separation method is reactive distillation. The reactive distillation is a new unit operation of chemical engineering. It combines chemical reaction and distillation into single process unit. That means here it is, in this one unit chemical reaction is also occur and distillation, that means separation is also occur. In reactive distillation both chemical conversion and distillation separation of the product mixture are carried out simultaneously. The idea of reactive distillation is old, but it is used for some outstanding application in the recent year. Reactive distillation is a process where the chemical reactor is also distilled. The separation of product from the reaction mixture does not need a separate distillation step, which saves the energy and material. If you think about the conventional method, in this conventional method reaction unit is also different, and separation, that means distillation unit, is also different. So in both different unit we need more utility. For the more utility, the energy consumption is also high. So that's why they are using the reactive distillation. This technique is specially used for the equilibrium limited reactions such as esterification and ester hydrolysis reaction. The conversion can be increased far beyond what is expected by the equilibrium due to continuous removal of the reaction product from the reaction zone. This is help reduce capital and investment cost and may be important for suitability development due to lower consumption resources. Being a relatively new field, research on various aspects such as molding and simultaneous process synthesis, column hardware design, non-linear dynamic and control is programmed. So this reactive distillation for the particular reaction depend on various factors such as volatility of the reactants and product, along with the feasibility reaction and distillation temperature. So this technique is very good, but we need some parameters. Based on the parameter, this reaction and separation is occur. So if the condition is satisfied, or that means the material selection of raw material is also important. If the material is good or based on the parameter, then separation is used based on reactive distillation. Otherwise separation and reaction is not done properly, so the yield is also not good in this reactive distillation unit. So normally in reactive distillation unit, two units are combined in one unit. So that is a very effective and good method for the separation. Advantages and disadvantages of reactive distillation. Advantages is increase the speed and improve efficiency, low cost, reduced equipment use, energy use and handling, less waste and fewer byproducts, improve the product quality. Chemicals are exposed to heat only once, reducing opportunity for the degradation. So that is advantages. And then disadvantages is that the condition in the reactive distillation column are sub-optimal or sub-optimal both as a chemical reactor and as a distillation column. Since the reactive column combines this, the introduction of an in situ separation process in the reaction zone or vice versa leads to be complex interactions between vapor liquid equilibrium, mass transfer rate, diffusion and chemical kinetics.